Today we are going to discuss about the Schmidt process that will help us construct an orthogonal basis from a regular basis that we found in a new vector space. So imagine if you end up falling into a new vector space, the first thing you want to find is a basis so that you can compute everything based on the basis. Now you want your basis to be as close to the standard basis as possible because being standard basis is very nice. So the idea is very clear. From a regular basis, construct an orthogonal basis. Then normalize the orthogonal basis to get the orthonormal basis. So if you start with any regular basis of k vectors, x1, x2, xk, then you can build up an orthogonal basis B prime of the p vectors here, following the instruction here. The first vector p is x1. The second vector p is the difference between x1 and a vector that is a scale of p1. And the scale is computed by x2 dot p1 divided by p1 dot p1. The third vector is going to compute it in the same manner. It's the difference between x3 and a vector that is a linear combination of p1 and p2, in which the scalars for p1 is x3 dot p1 divided by p1 dot p1. The scalar for p2 is x3 dot p2 divided by p2 dot p2. And you just continue this process. Very similar, you'll be able to find p4. And you'll be able to find the last vector. Of course, the last vector will be constructed based on the vectors that you have found in the previous k-1 steps. That's why you only have p1, p2 up to pk-1 here. Right? Just like when you compute p2, you only know p1. That's why you only can utilize p1. Of course, if you double check the dot product of any pair of vectors here, you will find that the dot product is going to be 0 always. So let me discuss what is going on here with you. Now you have one dimension space, the space that is spanned by p1, which you know is x1. Now then you want to find another direction p2, and this direction has to be perpendicular to the direction of p1, right? That's what you want to do. So you need to search for the vector p2 from the line that is perpendicular to p1. You know that you have x2, a different direction from p1. In order to construct p2, we are going to split x2 into the sum of two vectors. One is a red vector that surely we will denote as p2 because that is perpendicular to p1, which is what we want. And the blue vector, that is, as I said, the byproduct. I'm going to call it triple question mark because if I know this blue vector, then the p2 is actually just the difference between x2 and the triple question mark vector. So we dot both sides with p1 because the dot product has the distributive property, so we can distribute the dot with p1 into the sum here. So p2 dot p1 plus triple question mark dot p1. Now because we want p2 to be perpendicular to p1, so if p2 does exist, the dot product of p2 and p1 has to be 0. So that leaves us with x2 dot p1 equals to triple question mark dot p1. Because triple question mark is in the span of p1, it's in the same direction with p1. So it's got to be some scalar multiply p1. So that means we can go ahead and replace that here, rp1 dot with p1. Then by the scalar property of the dot product, we can pull out the R, and we end up having P1 dot P1. All right, so x2 dot P1 equals R P1 dot P1. So this implies that the scalar R is the ratio between x2 dot P1 and P1 dot itself. So the triple question mark is going to be the scalar R times P1, and the scalar R has been found to be this. So P2 is x2 minus the triple question mark. So it's x2 minus a scale of P1, and the scalar is this. All right, now you look at this formula, it's exactly the one here. So that's how we find P2. We now have a space W consisting of two vectors, P1 and P2. All right, so you have a two-dimensional vector space right here already, and the basis is an orthogonal basis, so that is good. Now you need to introduce a third direction into the picture so that you can expand from 2 dimension to 3 dimension. Remember, you have already used x1 and x2, so you cannot use them anymore, right? x1 is p1, so it's right here. x2 is actually just a combination of p2 and p1, so it's somewhere in the space here. In order to introduce a third dimension, you need to utilize x3. Now x3 comes into play. Of course, x3 is not perpendicular to p1 and p2, so x3 is not exactly what we want. It just helps us identify the third dimension here. So in order to get a vector p3 that is perpendicular to both p1 and p2, then intuitively we are going to seek for the vector p3 on the line that is perpendicular to the home plane W, which is the subspector space W, right? So you know that P3 is somewhere along the line here that is perpendicular to both P2 and P1. Remember, P1 and P2 has been perpendicular to each other from the previous step, right? So we are going to split x3 into the sum of the vector P3 that we want and the vector triple question mark. Now the fact is that triple question mark is inside W, which is the span of P1 and P2. All right, so that means that triple question mark will be able to express as a scalar times P1 plus another scalar times P2. So this immediately implies that x3 is equals to P3 plus R1 P1 plus R2 P2. So we are going to dot both sides with P1. Now remember that P1 and P2 are perpendicular to each other because of the previous two steps that we made. So this dot product is going to give 0. P3, if it exists, is going to be perpendicular with P1. So the first dot product is also 0. That means you can compute the scale R1 as the ratio of x3 dot P1 over P1 dot P1. Similarly, R2 is going to be the ratio of x3 dot P2 over P2 dot P2. So this implies that P3 is equals to x3 minus R1 P1 minus R2 P2. And that's equals to x3 minus the scalar R1 P1 and then minus the scalar R2 P2. What is R1? What is R2? You just substitute what you found here into the parentheses. So that's x3 dot P1, P1 dot itself, x3 dot P2, P2 dot itself. And this is exactly what you have here. You can repeat the process for higher dimension. Of course, we cannot draw any picture anymore. But the algorithm, the algebra still works, right? All right, so after k steps, you'll be able to find k vectors that are pairwise orthogonal or pairwise perpendicular. Those are P1, P2, P3, P4, and Pk. And this process is called the Schmidt process. Before we move on, let me remind you about something that I said before. So now it's time to mention about it again, to make it clear. If you still remember when we first learned about the dot product and orthogonality, we had theorem 6.4 that allows us to compute the coordinate of every vector inside a vector space W that has an orthogonal basis. If the vector is not in W, you're going to get something, and at that time I say in advance that something is the projection of that vector onto the space W. So let's consider this space W. It has an orthogonal basis, right? And if you still remember, these fractions are actually the coordinate of x3 if x3 were inside W. But because x3 is not inside W, these coordinates turns out to be the triple question mark, which is very clearly the orthogonal projection of x3 onto the space W. In R4, consider the hyperplane W satisfying the equation. So it's actually the space of all vectors of 4 components, x, y, z, and w, that satisfy this equation. Right? So in R3, you call it a plane. This is R4, it's the hyperplane. Find an orthonormal basis. In order to find an orthonormal basis, we are going to first need an orthogonal basis. Then we just normalize that orthogonal basis to get an orthonormal basis, right? Which means we divide each vector by the length to get the unit vectors. That's very simple. So the hardest part is to construct the orthogonal basis for W. In order to construct the orthogonal basis for W, we need to start with a basis, just a regular basis, but you need a regular basis to start with. So in order to get the regular basis, you will have to solve this equation or the system of one linear equation here to get all solutions. From all solutions, you kind of figure out the spanning set, and then from the spanning set, you get the regular basis. From the regular basis, you get the orthogonal basis, and then normalize it to get the orthonormal basis. Right? So that's our game plan. If you write the augmented matrix for this equation, then it's going to look like this. Because it's only have one row, so you don't have to do anything, right? You will know right away that this is going to be where the pivot variable is located. So this implies that x is pivot. You know that y, z, and w are non-pivot. Whatever non-pivot, you can set free. Right? After you set them free, then you can compute the pivot variable based on the non-pivot variables. In this case, the pivot variable is -1/2 y minus 3/2 z plus 1/2 w. So that means all solution x for the equation will be of the form -1/2 y minus 3/2 z plus 1/2 w, y, z, and w. Now you can rewrite them to find the spanning set. Split the y, the z, and the w out of each other. So we need to find a spanning set. That is step 2. So w is spanned by -1/2, 1, 0, 0, -3/2, 0, 1, 0, and 1/2, 0, 0, 1. we can go ahead and give them names: capital X1, capital X2, capital X3. And in this case, we don't have to find the basis anymore because they are the basis as well. These vectors are naturally independent because if you consider the dependency equation, then you will see right away the second line is going to give you A plus 0 equals to 0. And then the third line will give you B equals to 0. The last one will give you C equals to 0. So you can only find A, B, C being all zeros. If the scalar can only be all zeros, that means independence. So the next step, we are going to use Schmidt process to find the orthogonal basis. And we usually use the P because, you know, actually the P stands for perpendicular. According to the formula in the Schmidt process, P1 is naturally just set to be X1. Now then we have to compute P2. So P2 is going to be X2 minus a scale of P1. And that scale is computed by dot X2 with P1 and P1 dot itself. All right, so now we know that we have to compute X2 dot P1. All right, so what is X2? X2 is this guy. All right. So we know that if we use the dot product here, we have to rewrite X2 as a row and then matrix multiply with the column P1. So X2 written as a row is this. I use comma to make clear that they are not forming something like the number 10, for example, like this. And then P1. So when you dot them with each other, you're going to get this and this, so 3/4 plus this times this, so 0 plus this times this, so another 0 plus this times this, so another 0. So that's good. And it's going to be 3/4. All right. So we have computed the numerator here. Now we need to compute the denominator as well. So let's compute P1 dot P1. Now if you dot P1 with itself, you multiply this with itself. So that's going to give you 1/4. Then this with itself, that's going to give you 1. And then 0 with itself, so that's going to give you 0. And of course, the last part is going to be 0 as well. So this is going to give you 5/4. And so now we are ready to substitute everything we know into the formula. X2, this is X2. Right, negative 3/2, 0, 1, 0. And then you subtract by a scalar. That scalar is the ratio between X2 dot P1, which is 3/4, and P1 dot itself, which has been found to be 5/4. And then you will scalarly multiply this scalar with P1. P1 has been found in the previous step, negative 1/2, 1, 0, 0. And now it's just some computations. Yeah. All right, so the whole thing here, if you simplify it, you are going to get minus 3/5. Right? And so we are going to get negative 6/5, negative 3/5, 1 and 0. Okay, so next we are going to compute P3. So it's going to be X3 and then minus the scale of P1 and a scale of P2. Right. The scalar are computed by X3 dot. This is the scalar for P1, so you dot it with P1. and then divided by P1 dot P1. This is the scalar for P2, so you dot x3 with P2, and then divided by P2 dot P2. All right. So we know that we have to compute x3 dot P1 first. x3 is this guy, 1/2 0 0 1, and you want to dot it with P1, this guy. So 1/2 negative 1/2 is negative 1/4. This and this is going to be 0, 0 and 0 is going to make 0, 1 times 0 is going to 0. So it's only negative 1/4 here. And then you have to compute P1 dot P1. You already computed it, 5/4. Then you will have to compute x3 dot P2. x3 is this guy, right? Dot with P2, this guy. P2 is this guy. So 1/2 and negative 6/5. So that is going to give you negative 3/5. 0 with this one is going to give you 0. 0 with 1, 0. 1 with 0. So what you actually get is negative 3/5. And you will have to compute P2 dot P2. So this is the new thing you have to compute. Right. What is P2? It's this one. If you dot P2 with P2, you're going to get 36/25, 9/25, and plus 1. That is going to simplify to 14/5. All right, so you substitute everything and you get P3 equals to x3, which is 1/2 0 0 1 minus negative 1/4 P1 dot P1 5/4. P1 is negative 1/2, 1, 0, and 0 that we found, and then minus a scale for P2. That scale is x3 dot P2 negative 3/5 divided by P2 dot P2 14/5. And then P2, right, P2 we have found here. We just copy it down. All right, so straightforward computation is going to give you P3 being the following 4 tuple: 1/7, 1/14, 3/14, and 1. So we have found an orthogonal basis for W. All right, so last step, normalize. Now, if the question only asks you to find an orthogonal basis, then you don't have to go to the 5th step. You don't have to normalize. But if the question asks you to find an orthonormal basis, then the 5th step is necessary. And 1 is going to be just P1 divided by its length. The length of P1 is going to be just the square root of P1 dot P1. And because you have computed P1 dot P1, so you just need to utilize that, 5/4. So you put 5/4 here, and then you scalarly multiply P1. So this is going to simplify to 2/5, and P1 you have found to be negative 1/2, 1, 0, and 0. So the first normal vector, and 1 is going to be the vector. You multiply this to this, you're going to get negative 1/5. Then 2/5, 0 and 0. All right, of course, you are going to repeat the process for N2, and you repeat the whole process for P3. So this is going to be a simple step. Just divide every vector that you found in the orthogonal basis by the length of themselves, and you're going to get the normal vectors that you want.